हो गया शायद.
Yep. Let me check. Yep, चालू हो गया.
ओके.
अभी आपका वो जो एक्स वाला है ना वो नहीं दिख रहा, तो वो आपको वापस से डालना
हाँ,
पड़ेगा.
डाल दिया डाल दिया.
ओके, बस तो वी आर गुड टू गो.
ओके, बाय बाय. Yeah, sorry for that delay. I think we have the YouTube live as well. So yeah, with that, yeah, you can get started. Thank you everyone
Alright,
for coming.
everyone, we are officially live now.
Yeah, sorry for that delay. I think we have the YouTube live as well. So yeah, with that, yeah, you can get started. Thank you everyone for coming.
Okay, so this is our 12th session on the 12th of July, and I think number 12 is very interesting. I think there are 12 fermions on the stand model, but that's a different thing. Today, today with us tonight is someone who has just wrapped up his PhD from LMU Munich and the Max Planck Institute for Astrophysics, where he has been working with Hessian collaboration and major astronomy networks like LOFAR. So he's trying to decode the epoch of reionization. So in other words, you can say like he's studying the early light from the galaxies. So when the galaxies were forming and hydrogen gas like was going very faintly, and he listened that glow. He listened the 20 centimeter line, not just by like looking from the telescope, but in astrophysics, you have to know the machine learning, you have to know the simulations, you have to know astrophysical models. So he's doing with all that. So yeah, so he did his undergrad and master from Aizer Mohali, and yes, now he's completed his PhD, and congratulations on completing your PhD. And yes, welcome
Yeah,
to Zetagravit. Hello, Anshuman. Welcome
yeah,
to
yeah,
Zetagravit, and thanks for joining. And it's
yeah.
really amazing to have you here.
Mhm. Thank you so much. And yeah, we can proceed uh, as soon as you guys want, and it's great to be here.
Yeah, sounds great, Anshuman. So I think we'll just get started a little bit on your background, and I just want to ask you, we all, like to look out at the stars, but you
Mm.
are looking at a particular part of the universe which is just right after the Big Bang. So,
Yeah,
how is it that your life took you to this, kind of unique place? Because not many people get the opportunity to research such a different place in space and time.
yeah, yeah. Yeah, I mean, that's definitely it's when you're when I'm already in it, it feels it's hard to realize the uh, uniqueness of the situation. But indeed, it's quite interesting journey to be on, like to reach all the way till here from a variety of different experiences that shaped this journey. So uh, for example, I grew up like while moving around different cities, but for my high school, like around from 8th to 12th grade, I did it in Bhubaneswar, and I'm also from Bhubaneswar originally. So that was great. Like it was mm, your usual school life and everything. Um, but yeah, like I was, of course, like at that point of time I was fascinated with astrophysics and stuff. It sounded very cool, but I didn't know how do you go into all of that. And I was I was not even sure like what do you study during college to go into such a kind of a career. And on a whim, I had written the KVPY in 11th, and uh, around midway through 11th, when I actually had started looking into this, I realized that okay, wait a minute. Everybody around me is studying for engineering, but it from what I find by my own uh, like searches, it seems like I should actually study something in physics. Of course, engineering is possible, but physics seemed a better fit for the kind of stuff I wanted to do. And based on that, I was all applying to places, and eventually I ended up at ISER Mohali. And what ISER Mohali offered was that not only do they have a degree in physics, but they also really promoted us to um, go for internships during the summer breaks, so that we try to get a flavor of what kind of research happens. In the first, initially when I tried, I couldn't really find anything in astrophysics. When I applied to a bunch of places, but no, nobody was interested to take a first year student to like as an intern at that point of time. But I was able to find something in still in physics and condensed matter physics at TIFR, and I went for it, and that was definitely interesting. What I mostly did was pretty hands-on. It was hands-on electronics. It was also a bit of programming to analyze the data that we were collecting with high-speed cameras, and all of that was very interesting. But it also still solidified this fact that yeah, this is all interesting, but I'm still wanting to explore what is there in astrophysics. And that eventually led me to keep applying to places to actually get some work experience in the field. And that took me to the University of California in Santa Barbara the next summer in 2018. And there was something interesting in the sense that I was still trying to learn a lot of things. I knew how to do some basics of coding, but I did not know how to, say, for example, download specific software, specific packages, and make use of it. Do bash scripting and things like that. I was honestly not so great at programming with Python either, and my background in physics was also somewhat limited. But I learned from them gradually. With the professor I was working with, the postdoc I was working with, I learned quite a bit. And in the next summer break, I was able to come to Germany to the University of Heidelberg for a much more programming specific where project, again in astrophysics, completely different topic within astrophysics, but still in the field, just to basically get an idea of like, okay, earlier I was just building very simplified models. What about more complex models? And what about when we are doing really uh, uh, very intense data analysis, like for example getting data from models which have been run to simulate the merger of two black holes? That really gives a lot of information. How do we make sense of it? And that was quite interesting. But so far I was playing with models. So during my master's thesis, for which I was supposed to visit the Smithsonian Observatory at Harvard, but this was during COVID, so my visit was cancelled and I worked remotely. But there, what I wanted to do was to actually look at observational data, and for that I looked at X-ray astronomy data actually, and that was interesting. But overall, from all of these experiences, what I gathered was that I really like to see what we get from observational data, but I also am interested in how we build models and how do we basically interpret our data based on the models we have, and vice versa. How do we build models based on the data we have? Based on this, I started applying for PhD positions. And earlier, I had interacted with my current supervisor, and it seemed like what they worked on was quite interesting. But at the beginning, I had no experience in, say, your radio astronomy or running cosmological simulations. But what I did have was a lot of background in data analysis, as well as building my own statistical tools with, say, Python or C++, or even just regular bash scripting for some simplified software packages that I could call. And all of this was interesting. And based on our discussion, my supervisor was suggested that we could work on something with machine learning and this uh, uh, basically build techniques to find these kind of signals that we have still not discovered yet. Like we expect it to be there, but we know that it's extremely weak. So given our technology, given our capabilities of our data analysis techniques, we are getting closer and closer with each improvement that we do, but we are still not there yet. And that is indeed very fascinating. But I think it's like basically a mix of uh, being able to go for the next step, even if we are like at many points I would not be so confident in my abilities of what I can do, what I know, and things like that. But it's still interesting. So as long as it's interesting, it's there's no harm in trying things out, and that's basically what I went for, and it helped me go to a lot of different places, and that's been a very fun journey so far.
Yeah, that's amazing to hear. I mean, you've traveled far across the world in your pursuit of the stars. And I think that the PhD topic is something that you have stumbled upon is quite fascinating, right? So I know radio astronomy is, done across the world, and many programs exist across the world for such a thing. But
Yeah,
the epoch of reionization, right?
yeah,
That was your topic that you picked up during your PhD. So
yes,
let's get a bit more into what you did your PhD, because I think you just finished it. You're
yeah,
finally Dr. Anshuman Acharya right now, so
yeah, yeah.
congratulations.
Thank
But
you.
we'll start with that, right? Because our audience is here.
Mm-hmm.
And just before that, I just want to thank everyone for sticking around and joining us for the 12th edition of Zetagravit. Feel free to share this space with fellow space enthusiasts. And if you have any questions, please do leave them in the comments below, or stick around till the end of the space where we have a question and answer session with Dr. Anshuman Acharya. Yeah, so with that, let's get into the epoch of realization. Anshuman.
Yeah, yeah. Yeah. So basically, before going into the epoch of reionization, it is crucial to understand what we expect our universe to be like. So the current model of the universe that we have says that okay, we had something called the Big Bang, from which the universe began, and then it expanded very rapidly, and eventually it reached a stage where uh, the expansion was so much that the universe started cooling down, and it led to the first atoms being formed, the first atoms being mostly hydrogen. And this is the period known as the epoch of recombination, where we get the CMB spectrum that we see from satellites like Planck, because now that the atoms were forming together, the photons were not trapped by being hit around by energetic particles like electrons, quarks, and more. And they could actually escape from them because these particles had started settling down into atoms. So now, what we believe was the situation in the universe was that it was totally dark and was just filled with hydrogen atoms zipping around, maybe a little bit of helium and a little bit of, say, lithium and other elements as well, but mostly hydrogen. But because nothing was around, we refer to this period as the Dark Ages. But eventually, there were some collections of matter, dark matter mostly, into which baryonic matter, which is regular matter, started falling into. And eventually, we believe that stars, galaxies, and these things formed. And we believe that simply because in the modern universe, we see that all around us. So, if there must have been some period during which the first of these objects formed to reach the stage from just hydrogen atoms to a stage where we see all these stars, galaxies, and everything around us. And what is interesting is that, especially if we look at the galaxies that we see all around us, around our galaxy, the gas around them does have protons and electrons, but they do not have hydrogen atoms. These protons and electrons are staying separately. Or one could say that the hydrogen atom got ionized. So now you have the proton and electron in separate that are separate because of the energy being pumped into them which is coming essentially from the galaxies that are all around us. So so what we see basically is that now we have the modern times where we have galaxies everywhere with the gas around them being just protons and electrons and not hydrogen atoms, and a picture of the early universe where the universe was mostly just hydrogen atoms. So how did we get from one stage to the other? The idea is that the first stars, galaxies formed, say, around redshift 30 or something, which would be about 100 million years from the Big Bang. And this is what we call as cosmic dawn. And cosmic dawn starts the period that we call the epoch of reionization, because basically in the beginning of the universe the protons and electrons were separate, so they were ionized. Then they got together to form hydrogen atoms, but now they are being separated again by the photons being released by the galaxies. So basically they are being ionized again, and that's why we call this period when the first stars and galaxies formed and release these photons to ionize hydrogen as the epoch of reionization, because epoch just means a period of time. And around redshift 5, which based on our observations so far, we believe that this mostly ended, in the sense that we saw that most of the hydrogen around galaxies was ionized by this period. And this is still very early in the universe. This is 1 billion years from the Big Bang, or about, say, 12.8 billion years ago from present day. So this is a very early period of the universe, but it's still very fascinating. And we are trying to understand how this process happened, because we don't know how the first stars and galaxies formed, how fast did they form, how fast did different kind of objects form, like say active galactic nuclei, or something more exotic, say neutron stars or binary neutron stars, and pretty much everything fancy that we see today. How fast and how quickly could they form, and how many of them formed during this period is important. And there are two ways we can study it. One is by directly looking at galaxies one by one and seeing their properties. This is difficult, again, because this is so early in the universe. So we have to really look for those galaxies from our data and have very sensitive telescopes. But we do have something like that. We have JWST. It's at least able to find the most brightest of these galaxies. But then there are so many galaxies. We can't just keep going one by one looking at each galaxy. The opposite side of this is to look at the gas, the hydrogen gas around these galaxies, which this gas we call as the intergalactic medium, because it is the medium between galaxies. And the only way we can do this is by looking for any kind of signal that would come from just hydrogen atoms. But what would an atom radiate? That's a very important question, because for radiation you need photons, and just a photon would not radiate much. But there is one solution to that, and that is the Tornado signal, which we can look at with radio data. And that is what I've mostly focused on, to assist the LOFAR collaboration to look for this Tornado signal from this period, by improving our techniques to look for this, as well as building better models, so that, okay, once we have a detection, how do we interpret that detection? And that was the crux of it, of my PhD, essentially.
That's amazing. Like it's very interesting to know how these ions form into hydrogen atom and how this hydrogen atom combine into different elements of periodic table and how all these things were formed into galaxies and stars. So you said that the 21 centimeter line is one of the way by which we can basically find out how this universe formed.
Yeah.
So, can you give us more glimpse into how 21 centimeters are formed and how we are detecting it?
Yeah, sure. So, in general, the 20th century signal is referred to as a forbidden transition, because this is a very, very, very weak signal. The 20th centimeter refers to the wavelength of the signal, and that pushes this to essentially in the radio wavelength territory of the electromagnetic radiation spectrum. But how does this come about? Well, when we look at a hydrogen atom, we have a proton and an electron, and both of them can have an associated spin. they would have basically a magnetic dipole moment that would be associated with the spin. And if the spins are both spin up states, then this magnetic field adds up. And when magnetic fields add up, they are basically creating a sense of motion for the hydrogen atom, because with if there's any mismatch with the magnetic fields around it or anything like that, it would experience motion. And the ideal way for the atom to stick around would be to lose this energy. And that is what most of things want. They want to be in a lower energy state. So usually you would say that, okay, instead of both being spin up, say the electron flips to become spin down, and now the magnetic fields cancel out, and it will be at a lower energy state. But this difference is a very small energy difference. It's while electron volts are already a very small energy measurement, this difference of energy between the uh, electron having a spin up state to a spin down state is in micro electron volts. And so what in general, if you have, say for example, if you have a box of hydrogen atoms in a in say a laboratory in on earth, you would see that you do not really see any photons being produced for going from one state to the other. Instead, these atoms would collide with each other and basically balance out the energies based on that. However, we have such places in the universe where this gas is very diffuse. And secondly, we believe that the intergalactic medium is also very diffuse. By diffuse, what I mean is that it basically has, say, about one atom per meter cube volume. So now atom is quite alone. It cannot collide with another atom to exchange energy. Then the only thing left for it to do in order to lose energy is to essentially radiate a photon. And this photon has a wavelength of 29 centimeters, or a frequency of say 1420 megahertz. And now, okay, one atom produced one photon. Why do we care? Well, as mentioned, hydrogen was ubiquitous in the universe at this early periods, and even now, if we look at diffuse, cool gases in, say, within a galaxy, we still see hydrogen atoms in quite a lot of amounts. And thus, we eventually have a state where we have a lot of these atoms radiating a lot of these photons. So eventually, there would be enough photons to have a detection. And if in the early universe, if it was mostly hydrogen atoms all around the first galaxies, then eventually there should be enough photons so that we can detect it. And that was the basic idea, that this is why we can use the transcendent signal to look for signals from the epoch of reionization.
Aikana.
Goes deeper and deeper into the radio regime, we could basically look at things across redshifts by looking at the radio frequencies across different frequencies. And that's why it has turned out to be a very important resource for astronomy.
Damn, like one atom in 1 meter cube is very small, and I like these signals are very faint. So, like, how we are able to detect it, and what's the major challenge which we encounter? Is it the detection or extraction?
Yes, so if I like, I would suggest, say, like, I think on the YouTube shares thing that you're showing, maybe you can go to the next slide. There is a plot that's very interesting in I think slide number 7 or something, which is very useful to basically give the picture. And that is that we essentially have, from like, we can see the 20 centimeter signal from within galaxies around us, but we are not able to find the 20 centimeter signal yet from the intergalactic medium, at say redshift between say 6 to 25 or whatever, which is where the epoch of reionization is. And this is because the signal, as you said, is incredibly faint, and there are many more sources which are in between us, between these redshifts, because we are trying to peer into a period of the universe which is almost 13 billion years ago. So it is hard. And what it basically means is that we firstly have to gather lots of data. We need really sensitive instruments which are able to gather lots of data. But we as additionally have to analyze this data in a very careful manner to be able to separate out the signal from all the other kinds of signals in the data, as well as inherent noise in the data. So for example, in this like if the people on YouTube can probably see the plot, it basically shows a power spectrum at large scales, which essentially says that how much does the transcendent signal vary across scales of say 10 megaparsec, or which is pretty huge, because um, our galaxies are are sized at kiloparsecs. So this is measuring the 20th century signal at very large scales. We want to see how much it varies, and we have models which suggest that okay, the variation would lie, if you measure it in temperature, it would be about 100 millikelvin square, because the way we calculate it, it comes as a square of temperature. But even our best like measurements, basically what they say is that the signal is definitely weaker than say 1000 millikelvin square, but we don't know where exactly it lies. uh, we believe that if you could just observe longer with existing telescopes like LOFAR and NENUFAR, like right now we have about 140 hours of observation, but instead if we had 1000 hours of observation, maybe we would be able to detect the signal. So in that case, detection sounds simpler. It just needs more data. And of course, it needs a lot of time for us to process that data, because the data is not so simple. There is variation in how the data behaves from one night to the other. So if you measure, say, 6 hours on one night and 6 hours on another night, the way you process the data can be completely different. Uh, and even so basically detection is hard, but it's not the hardest step. It just needs more data. But extraction is even more difficult, because not only it requires us to have a very careful understanding of what are the contributions of the different things that are in the way, but it also needs us to have a very good understanding of how our instrument through which we are collecting the data, how does that behave. Because any kind of noise that it adds, we need to be able to identify it and separate it out. And doing that is extremely hard. And thus, it would be basically boiled down to say that we are improving our ways to extract the signal so that we don't have to rely on just spending a lot of time on just observing data, processing it. But in theory, if extraction and detection were both equally probable, we would say that detection is still easier because it just needs more data.
Yeah,
I
quite yeah, interesting, Anshuman. What I will say for our viewers on YouTube, and especially because the graph is there,
Yeah.
I think a lot of them might not be familiar with some of these abbreviations, right? So you have
Yeah, that's
a
true.
lot of these things of LOFAR, SCA, Nenufar. So let's get take a step back, and maybe you can walk us through how you detect in astronomy, right? What are the different ways,
Yeah,
and then we can walk through that, and then we can come back into how we process these signals, right?
yeah, yeah,
Because I think you said these are very faint signals, and it will take a complex type of processing that will enable us to kind of understand what is the signal amongst all the noise.
yeah. Yeah, so uh, basically, we have been building various radio telescopes, and these radio telescopes, they operate essentially as interferometers. So, what interferometers do is that um, they have many small radio telescopes working together to observe the same patch of the sky, and the distances by which they are separated essentially becomes the size of the radio telescope. So for example, you could have multiple radio antennas which are separated by 1 meter square, or just 1 meter. Then if you add them together in say along one line, they could, and you have 10 of them, that acts the same as a 10-meter wide dish, but not having the issues of basically uh, handling and maintaining a full dish. You basically, you can swap around, you can change how these small antennas function. And that's what we have been doing. And that's the principle behind LOFAR and NANOFAR. They have fixed antennas. You cannot point them around the sky, but they look up directly to the sky. Um and whatever passes over them, they could either focus on that, or you could basically ensure that they are pointing towards a specific patch of the sky. So while you cannot have full maneuverability, you could at least, whatever is visible across from one horizon to the other, you could um, fix that. Okay, this part can be looked at. So that's something that we do with LOFAR and NENUFAR. And SK does that for SK low. But SK mid is something that is more similar to, for example, ALMA or GMRT in India, which is that it has proper dishes, small dishes, not extremely big, but still, it's say about several meters in diameter. But these can be maneuvered a bit, and they use this instead to basically have greater ability to pinpoint different sources of the points of the sky and look at it. For example, in India, we have had such radio telescopes, like I mentioned, GMRT, which uses around 30 of these dishes, where they can pinpoint it to any point of the sky, and they look at, say, a specific wavelength, which is usually, I think for GMRT, it is the lowest radio frequencies that are possible. And they basically designed it in such a manner that eventually, when we build larger variations of such, we would be able to replicate what GMRT does, and that's what we would do. And essentially, this is what SKA is doing. So SKA is doing something similar. It's spreading these dishes across a square kilometer area. So not 30, they have several hundred of these. But the design principle still remains the same. Apart from that, you could also have something similar, which is not lying flat on the ground with just one antenna. You could have a some amount of maneuverability, but not too much. But then it allows you some stability. You do not have you do not have extra instruments to maneuver things that much, but still have a little bit of them. And that is cylindrical antennas, which is where you have a half a cylinder just put together to point at the sky. And that is also something that India has done. I think this is the Uti radio telescope, and even Canada has their own called Chime, and others such as like that. And all of these, the basic idea is that we are looking at specific frequencies, and they're trying to receive those frequencies. That is fine. But when you have just a frequency, you are not really uh, fixing yourself down to any specific sources. So what we have to do eventually is to be able to identify how does like how much of a contribution does different sources have per frequency, and then we try to model each of these. And a way to do that is basically to take a Fourier transform of this data that we get. Like if you look at this data, it would be, the what the radio telescopes get is essentially a 2D map, because they are looking at the sky, and we just get a patch of the sky with different intensities. And what we could do essentially is to do a Fourier transform, and it gives us an idea of, okay, for each frequency, how strong is the signal across this patch. And this Fourier transform gives, by looking at it, we are essentially generating a power spectrum. And this is where we focus at, because the power spectrum gives us an overall picture for the patch, instead of having us worry about, okay, how was the, like if I'm looking for the 20th center signal from Epoch of Reionization in this patch, how does it vary from one corner to the other? This is very difficult. But if we have an overall idea that, okay, in this entire patch, it is strong at scales. If we measure the corners, it is the variation is more, and if you measure right in the middle, the variation is less. Then that is something simpler, because it's not looking at everything overall, but is everything one by one, but it is looking at things overall. And that is what people I was pointing at. It was pointing at a power spectrum, and all of these telescopes like LOFAR and NENOFAR, which have already been developed, and SK, which is currently being built, is trying to look at this patches of the sky and then converting it to power spectra and look for what could be the Tornado signal and what could be contributions from, say, radio emissions from AGN, radio emissions from the Milky Way galaxy, or even from the ionosphere, which is this layer around the Earth's atmosphere, where high energetic particles interact with the Earth's magnetic field. So all of this has radio data, and we have to identify and subtract them one by one.
Oh, I see.
Yeah.
So basically, there are three parameters which we need to take care of. So first one is the frequency, like it should be 1420 megahertz. The second part would be to like analyze the amplitude, like how bright our source is. And the third part being redshift, like from how
Yeah,
far the signal is coming. Because like we can artificially also generate 1.42 gigahertz signal. So
yeah,
those three components are important. Okay, so
yeah,
my next question is, so like this radio telescopes are very sophisticated instruments. So I
yes,
assume we need many different interdisciplinary people to do it. So we need
yeah,
electronics people, we need mechanical people to fabricate and build this
yeah.
like those gigantic mounts. So how
Mhm.
does AI comes into like this thing? So how, with the help of ML, you like connect the extraction part in the
Yeah,
astronomy?
yeah. Yeah, so as mentioned, like even now, right now, SK is building so many telescopes for their interferometer network. We have lots of engineers employed for like electrical engineers, mechanical engineers, but also for each of these steps, there is also the role of computer science, because every time you are, even if you add an extra interferometer, like if you want to distribute the interferometers, do you put them in a square, do you put them in a circle, like how do you distribute these radio telescopes around each other, is very important. And uh, it basically adds up noise, in the sense that the way one telescope operates, uh, because it's a machine which is receiving signals from us, it will produce some stray radio in a emissions, which will affect the, maybe it will not detect it by itself, but it will affect the radio telescopes near it, because we are building a network of these radio telescopes which are all together. And we really need to model this noise and everything. And this is for this phase, the planning phase itself, we needed computer science to build models, like simulations of telescopes itself and how do they behave, to have an idea of what would be the optimum way to measure this, and secondly, to build improve filters to essentially mitigate this noise. But the most important part where machine learning really has started helping us is signal extraction. And this is because the basics of machine learning that people have always used it for is pattern identification, which is to see that, okay, if you have lots of data, then how do I find some specific kinds of things in data? For example, the popular example that people give is that how if I am giving some machine learning algorithm a bunch of pictures, how would it know which are the pictures of a dog? Um, this basically translates to, if you translate it to radio astronomy, to my work, it translates to, if I give it lots of data from a radio telescope, how would it identify that, okay, this is the Tornado signal's power spectrum? And that is just basic pattern identification. We have lots of different machine learning algorithms that do it, like autoencoders, and even basic principal component analysis also assists in that. But the second part, which also comes from machine learning, is pattern representation. That is, to if you are able to identify that this pattern exists, how do you, like, why exactly does that pattern, like, what is the source for this pattern, and what is the underlying parameters that contribute to such a pattern. And that essentially is the basis of curve fitting, or basically finding an equation for say a distribution that you're seeing. So that's also something important, and something people do. But in my case, that was the most important part, is signal extraction. And that is because we do not know for sure how well are we modeling all the different sources that can contribute to the radio data, as well as all the different sources of noise. So if we have a really nice machine learning algorithm that knows what the 20th signal looks like, we will be able to extract the signal from all of this. And even if our models for identifying what is noise, what is coming from the Milky Way galaxy, what is coming from other galaxies, is not so good. So this is what we have used it for, but this is all observational data. We have not really talked about models yet. And a very important part of astronomy is also to be able to build models based on the physics that we know. So if we have the physical laws, how can we build a model which generates an output which essentially looks like what our telescopes look at? And all of this process is very fascinating, and it is doable, but also very expensive, because we really need to, for example, if you want to model a night sky with lots of galaxies and stars and everything, maybe your simulation can show you the galaxies, but can you use the same simulation to look at the stars within the galaxies? You could, but the cost of running such a simulation is massive. Even the biggest supercomputers on Earth cannot uh, handle that much data at once. So we are now focusing on trying to get around this problem, and this is basically because of the advent of things like generative adversarial networks, which is already kind of old news now, because now the newest things to do is diffusion modeling, which in popular applications has been to generate images or videos. So, for example, you give it a prompt or whatever, or if you give it a, say, for example, a low resolution image, you tell it that give me a high resolution image, or give me a different image based on this image. And diffusion modeling basically works on taking all of that information and adding uh, the required information that you seek. So what we are now working on is to speed up these model generation times. Like, instead of running it for months and months together, can we make it faster, as well as to super resolve these models? For example, I don't want to run a model which is good for looking at the intergalactic medium with all the galaxies, and then, but it's not good for having the stars within the galaxies. So why not use diffusion modeling to add those stars within those galaxies by training it on actual like smaller models, which just say you model just one galaxy, so that you can have the resolution to have the stars in it. And then you learn from this such simulations, and you take it to add these stars in much bigger models which have thousands or millions of galaxies, and each of them can now have stars within it. So we would not just be modeling galaxies, but be stuck there, or just not just modeling stars within one galaxy, but we'll have all of them together. And this is what a lot of people are working on. There have already been some updates based on this. And what people have been pushing for in the last, especially in the last 2 3 years, is for a much greater interaction between computer scientists, data scientists, and astrophysicists to learn from each other and build more physics informed AI based tools to improve our way of modeling and understanding the universe around us. So yeah, there's like a lot that can be done.
Yeah, like these are like some of the best kind of insights which I have heard so far, which are like related to how CS is like used in astronomy. So I really want to thank you for sharing it. I'm sure many people who are into the CS background, will be surely inspired to pursue astronomy after hearing this. So, like before moving to my next question, I want to thank our audience for sticking with us. Like there are many interesting questions which Sir is going to answer, and at the end you can also ask him question if you have any. So do stick with us till the end. Okay, so moving on to the next part. So whenever a newbie is introduced with the astronomy, what he or she knows is 21 centimeter line. So now my next question is, what's beyond 21 centimeter lines in radio astronomy?
And that's that's an interesting question. So, um, I mean, if we are looking at just the high redshift universe, the transcendental line seems to be the like one of the only ways. But in general, like if we are looking at say galaxies around us or AGN around us, they emit across the radio frequencies. They have um, thermal Bremsstrahlung radiation and things like that, which are essentially any kind of radiation which does not have that much energy but is still being produced. For example, an active galactic nuclei is essentially a very supermassive black hole within a galaxy, and it is accreting matter. And while accreting matter, what it's doing is it is churning that matter around it. And when you're like basically whipping all of this material, rocks, dust, everything together around a supermassive black hole at extremely high velocities, they would be rubbing across each other. There would be friction, and that is generating energy. And this has to come out somehow, and it will come out in the form of radio data, radio emissions. And this is one way, but there's also something very interesting, and that is that you expect to see, for example, optical or UV radiation from some galaxy or some quasar or anything, but there is a lot of dust or something in between you and that galaxy. Now, what the dust is going to do is essentially absorb this radiation, and the radiation would then be just heating up the dust. And you can see this heated up dust in the form of radio emissions again, because while the specific high energy photons, so the photons at higher energies in this where high means just optical, are not reaching you, they're them reverberating through the dust is generating radio photons instead, which you can see. So what it would give you essentially is like this dust, this heated up dust, is to show how much of diffuse um, uh, ordinary matter is there between you and certain objects. And that is very important because while we can see the ordinary matter which is glowing in the form of stars and galaxies and everything, all of this dust, gas, everything, it's very hard to look at it. And if we don't know how much matter is around us, it is very hard to build models of the universe. Like say for example, the lambda CDM model says that we would have this much amount of matter, this much amount of dark matter. How do we verify that amount? We can do that by looking at all of these telltale signs from these very um, uh, faint sources which are just emitting in radio. And lastly, you would also look at stars, most importantly our sun itself. And the way it emits in radio is a very good measure of how the solar corona behaves, which in turn gives us a very good measure of how the magnetic field of the sun behaves. And thus radio astronomy, where you're focusing on the sun, is a very good tool to understand when does the sun's magnetic field have variations, which is a good way to know when there would be solar flares, when would there be uh, big coronal mass ejection, which could lead to, for example, seeing aurora, or even if it's worse, we could even knock out some of our networks, like for electricity and such. So all of this is very important, and because everything in the universe has a little bit of energy that it could emit, we can essentially see the entire universe in radio. So beyond the 20 centimeter, there's also the entire frequency, and there's a lot of ways in which things can emit.
So you said that we can see the whole universe in radio, waves. But like in astronomy, they are way bigger, right? So there is gamma rays, there is
Yeah.
infrared, but like most of the uh, window is like on radio and optical. So why we ignore other frequencies, like other signals? There is infrared, there is gamma ray. So why we are so obsessed with these two windows only?
I mean,
And
yeah, to be fair, like now we have JWST, which operates in infrared. So it's not something that was ignored per se, but it was basically that because radio waves are so low in energy and because they have large wavelengths, they are able to penetrate through the atmosphere quite easily because they're so low in energy that uh, they do not have that much energy to give, and they can just drift in and we just see it. So if you just have something on earth, like a dish on earth, it would just be able to observe in radio without any problem. So one of the key reasons why radio was so popular from the very beginning and even now, especially now in fact, is that it's so easy for us to develop something on earth to observe in this frequency. And similarly for optical was something that was more straightforward. We could It's something that we see in. So just building bigger and bigger telescopes seemed like a very straightforward way to observe in this. um, and between radio and optical, we also have infrared and microwave territory, and it was unexplored for quite a long time. And we did have the Spitzer telescope at one point, but it did not perform as well as was expected. But now we have JWST, so that is covered.
so
At higher energies, the problem is essentially that these photons have much lower wavelength. So if you have less wavelength, you have higher chances of interaction, and they would thus be very very difficult to firstly find those photons, and secondly to that it should have actually reached us instead of just interacting and then going somewhere else. And secondly, to develop sensitive enough telescopes for this. And because these don't make it down to our surface, because Earth's magnetic field would deflect away such high energy for photons, and they would anyway interact with things. We need space-based telescopes for them. And for that, since the 1990s, we had Chandra, which observed in X-rays, and then we had follow-up telescopes, and even now we have some like XMM Newton and Swift. But yes, it is hard, and it would be nice to have more X-ray telescopes, um, because there is still a lot that can be done. And gamma rays are even much more high in energy, so it's a bit harder, but efforts are being done. A
yeah,
very crucial window we are missing now is UV, because Hubble, which looked at the UV side, is also getting older. So we would have to see how things go.
yeah. So like radio astronomy is the king of whole astronomy. So now coming back to radio, so you have mentioned that how detecting the 21 centimeter line is not only hard part, but there is also huge mess of foreground noise. So
Yeah.
so how you like do that? Like how you extract the
Yeah.
data from those foreground noise?
Yeah. Yeah. So basically, when we talk about foreground, we essentially say that, okay, if we are looking for the signal from redshift 10, then what is the data that is in our observations from the radio telescope, which is coming from things between redshift 10 to 0? That is our foreground. And what in this scenario, what happens is that basically, because redshift 10 is so early in the universe, there's almost everything that we can imagine that is there in between. So we have not just contribution from the ionosphere of the earth, but also from the Milky Way galaxy, from surrounding other galaxies and AGN and such. But the good thing is that overall like we can model firstly a diffuse emission of radio, because if everything is emitting in radio a little bit, like I said, then this could all add up together to become like a uniform background of radio. So we could first model that. But then there could also be very bright sources in radio. For example, uh, you would have supernova remnants, like something that has exploded as a supernova but still has enough energy left to slowly radiate it away in radio, or some galaxies which just have a lot of radio emissions, like Seyfert galaxies and things like that, or AGN. But these would be bright pinpoint sources, and we could then look at, okay, this is the source, this is the properties of the source based on not just observations from this radio telescope, but also observations from other frequencies. For example, we could observe from optical telescopes and others to know, have an idea of what kind of physics is going on, to essentially build a model of what this point bright source contributes. And we then look at the patch of the sky we are looking at and identify each of these points, understand what kind of things, what how much contribution they have, and how much of the overall contribution from low energy sources has to the uniform background. And then we subtract all of these contributions from the data, so that what is left in the data is the 21st century signal, if everything is perfect, and all the sources of noise that are there while collecting the data. So the noise could just be heat from the radio telescopes while they were collecting the data, or just the way these radio telescopes store the data, or the interactions between different telescopes within the same interferometer network.
Okay, okay. So I think before moving into the second, like next questions, which related to careers, because like
Yeah.
we are like it's been like 50 minutes plus. So I think.
No. Yeah.
But before I have a question like related to your work. So
Yeah.
so you working on something called Polar.
Yeah.
So like you need machine learning on the all that. So like can you tell me about more about this Polar thing?
Yeah. So Polar at the moment was essentially, like, just to put it simply, we you can build like models of the universe in many ways. The the most direct way would be to take all of the physical laws and all of the things in the universe together and model it at once. For example, you take uh, a model, you put it in dark matter, you put in ordinary matter, you put in dark energy, you put in everything together, and you evolve it across time. But given the scales at which we want to model, like, say, a patch of the sky, which in terms of volumes is even much larger than galaxy clusters. It is, say, 200, 300 megaparsecs in scale. So it is very hard to model all of the physics together. So the solution to this is to do things in a step by step manner. And Polar does exactly that. What it does is that it first runs a dark matter only simulation. So we just take dark matter particles and we put in the equation of gravity and we see how they interact. And we run it from the starting time to the ending time that we want it to run. Then what we do is that we use another code to add ordinary matter into it. So how do galaxies form within these like along with this dark matter particles? We paste it into it. We see how do stars form, how do supernova explode. We add all of these physical prescriptions and let it just run one more time through the start to the end. But all of this is fine. We have matter, we have dark matter, dark energy has been taken account in the first run, ordinary matter has been added. But the lambda CDM model has one more thing, and that is radiation. And that is the last step. We need to add actual photons into this simulation. And that's why what Polar does is that in the third step, it says that, okay, this is where your galaxies are. Now, this is the mass of the galaxies. So, based on our physical understanding of how masses of galaxies and how much photons they produce is, we it assigns that, okay, from this galaxies these many photons are being produced at these times. And then it evolves it across time to see how would the photons go around the simulation, how will they interact with hydrogen atoms to essentially ionize them in our simulations. And thus by the end of it you have a fully physical model. Maybe it's not perfect because in reality dark matter has some interactions with ordinary matter has some interactions with radiation, and so on. And we are approximating that by, because we are doing first finishing dark matter fully, then finishing ordinary matter fully, and then radiation. um, but it's still something better and something that is doable, at least given the scales of our supercomputers. And that's also very important because we want it to be run for enough duration and give us enough data, so that not only can we look at the Turner Center signal, which is of interest for radio astronomers, but we also look at observational data with in IR, like in infrared, in our when we measure it with our JWST. But when it was produced at the UV frequencies. And with this, what we can do essentially is that with the same setup of polar, we can look at not just data from radio telescopes, but also from JWST, Hubble telescope, and all of these. And that would be very helpful to basically understand the universe by having the same model being compared with all of these different observations. And this is where AI steps in, and that is that we have we have developed this model. It works great, but it still does not have the resolution to have the smallest galaxies, the things within galaxies within it. And this is where we have started developing a diffusion modeling based approach to add these features by doing super resolution. So for example, if the first galaxies, we expect that okay, it would have formed big galaxies, but it would have also formed small galaxies. So how do we put these small galaxies within it? And that is how we are adding it into this basically into this this simulation model.
Yeah, so
Understood.
that's
Yeah.
really interesting. But I think we are running behind the time. So
Yeah.
we will move forward to like questions from the students, because like most of the students are watching this, and people like me in
Okay.
their first or second year of college, like they're like
Hmm.
I love astronomy. I am obsessed with these things, but these things are not like things like it's not like you are looking at the picture. You need to do lots of coding. You need to do lots of simulation. You need to learn
Yeah.
Python alone. It's not just like JWST picture. So,
Yes.
so like if someone in their like school and they are in college first or second year and want to start career paths in astronomy, and like most of them are from India. So what kind of
Yeah.
career paths actually exist in India?
Yeah, that's definitely a very good question. And in general, getting into astronomy, the most common things that in India people do is either a degree in engineering, but if you can, I would always be happy to recommend that you also consider a bachelor's in physics, because in the end, while you are using a lot of engineering techniques, they are motivated by the physics behind it. But if you are doing a bachelor's in engineering, that is completely fine. It can be anything. It's great if it is computer science or electrical engineering or even mechanical engineering, because then you can directly connect it with things that are being done in astronomy. But it doesn't matter too much what kind of bachelor's degree you are having. What you can focus on is to then do a master's degree in physics or astronomy or something like that, if you're interested to go into, say, theoretical, like this, simulations, modeling, all of this, or observational astronomy, by doing a PhD in physics or astronomy. You could also, for example, even if you come from a bachelor's in physics, MSc in physics, PhD in physics, you could be doing that PhD and beyond in instrumentation, which is to develop these radio telescopes, to develop the instruments that collect this data and all of that. But it could also be very interesting for you to be involved in, for example, collecting these kind of data, or like building instruments that collect these kind of data, by supporting such observatories, telescopes, and everything as engineers. So for that, you could go from a bachelor's in engineering to, and say, an MTech or something, and directly go into instrumentation. Some people who have also done like a bachelor's and master in physics realize that okay, astronomy is great. I like the observations, but I don't want to really go into the details of measuring these data and making sense of it. I want to just focus on the instruments. So they could also either do a very instrumentation heavy PhD and then go into instrumentation, or even do a MTech, which is in India, for example, a lot of places which offer an MTech, they accept PhD, MSc physics people as well. So that is also an option. And then if you if you for example look at the different institutions in India, there is actually quite a lot of them. For example, for theoretical astronomy, there are, of course, research institutes like IUCA, TIFR, IIA, which have a lot of people. But there are also universities ranging from national level ones like IISc, ICERS, NICER, IITs, NITs, but also state universities, private universities, and many more, which actually do employ astronomers. For observational astronomy as well, all of these institutions do have them. But we also have more observational focused places like NCRA, which operates GMRT telescopes, ARIES, RRI, and many other such observatories. The instrumentation part does involve astronomers from all of these different institutions and universities. But additionally, there's a lot of interesting work that is being done by, for example, PRL, or even at RRI, actually, in particular, they do a lot of instrument designing. And there are also various labs which are affiliated with ISRO. It may not always be for technology which is used for astronomy per se, but it is all about improving space technology in general. And BARC also has some people involved in almost all of these aspects, including instrumentation. There are other more niche institutes like RRCAT, which are involved with this. But basically, it boils down to having a bachelor's and master's in uh, physics or engineering, and then going into a PhD if necessary, or going for more engineering specific roles. So there's a lot that can be done in India itself, and but I would also, of course, encourage you that if you get an opportunity to also explore things beyond India as well, because astronomy by itself is a very highly collaborative field. Uh, for example, India is part of the SKA collaboration for the radio telescopes, and we have not just a lot of people in India, but we also have a lot of Indian origin people across the world who are collaborating, contributing, and working together for this collaboration.
So yeah. So like just a quick shout out to everyone who is watching. I know there are school students and some undergrads maybe, and even postgrads folk watching this. And I'm really glad that you guys are watching this, and thank you for being curious and showing up to listen to something like which is very deep. So I think we are running with time apart. So can you can take this from now.
Yeah, sure. Thank you. So my question is, so CS and astronomy are like, I know they both are related somehow, but majority CS people know how to run or create this Python model, or let's say some C++ code. And on the other hand, they don't know astronomy. But
Yeah.
same goes with the astronomers, that they know astronomy, they know physics behind it, but they don't know how to code in most of the cases. So what they do is they basically find some libraries or ready-made tools. But when we are doing hardcore research, like let's say we are like discovering something for the first time, then we need to build this tool from the first principles of like building things. Like we need to build these tools from basic laws of physics. So what do
Yeah.
you think? What can be done in this situation?
Yeah, this is a very commonly discussed problem in astronomy, that astronomers write a lot of code. Like there is a very high amount of code out there that they are producing, but the problem lies is that they are not taught how to code. They have just learned how to code based on their requirements. So the ability for them, for it to be usable by, for example, if one person writes a code and then they leave astronomy and somebody else has to take over, the ability of the second person to understand how the code was developed and why it's written the way it is limited, because the first person did not do enough documentation, or they did not follow all the required checks and balances that are necessary. For this, there has been like a lot of discussion in trying to work more closely with computer science scientists and uh, have a better interplay between these people. But at the same time, there is this push that yes, we can, like, okay, we can code to a certain amount. Then how much of an involvement do we want from the computer scientist community? Do we want them to really get into physics? Like, for example, if it's someone who has a bachelor's in astronomy, bachelor's in computer science, should they do masters and a PhD and then continue, or should they be just hired as an engineer and they just like continue to be at core a computer scientist? So people are trying to approach it in different ways. There has in recent times been a push to have both of these aspects, um, to basically encourage undergrads to, even if they are a bachelor's in computer science, to apply for astronomy internships and things like that, so that they get a flavor of, okay, what kind of problems exist, so that even if they do not understand all the concepts, they have a fair understanding of what kind of problems exist in this field, and with their skill in computer science they can contribute, like immediately start contributing to it, and eventually pick up enough knowledge of physics to be able to become an astronomer. This is one way. But the second way is to just be hired as an engineer, and this is not the most common yet, but there has been a push for doing this as well. So at the very least, people are setting up IT and computer science departments for astrophysics and astronomy institutes. But there has also been a push to hire like engineers, essentially to go through the codes, the massive simulation codes that we build, and improve them, see how exactly can it be made smoother, how can it be made more modular in order to be usable by a larger group of people. And for that they are also hiring computer scientists. So as if for people who are undergrads as computer scientists, I would just say that for now, if you are interested in astronomy, write emails to professors expressing your interest to work with them, and just go for it. Like, it is okay if you don't know all the physics. What you are bringing to the table is your knowledge in computer science, and what you learn through the internship would be the physics that you need to know in order to work in astronomy. And based on that experience, you would know how to proceed further.
So yeah, so I think I have one question related to this mail thing.
Yeah.
So it's like cold mailing is some kind of art. What do you think about it?
I mean, the main point is that it should not, like, when we say cold mailing, it feels like it's a generic email that is okay, but it should be like, even if 80% of your email is mostly the same structure, there should be 20% which is where you have actually gone through the professor's website, or what topics they work on, or once you have enough knowledge of astronomy, you should also look at their recent research papers, um, and you mention about them, and you express that you want to, like, essentially work with them. It should not be like just something generic that, like, you without the seeing their name on it, they would not know that, okay, is this addressed to me or not. And additionally, you should also have, like, you attach a CV. It is okay if it's just one page, or even barely fills one page. That's not a problem. But having your information in a uh, presentable manner, not any, it should not be anything fancy. It can be simple, but as long
You have sent to professors and how many replies you have got
I mean, during my undergrad
in
and
your
also
college
for
time.
looking for my, like, doing my master's thesis elsewhere, I think overall I sent, okay, there were some back and forth emails. There were some people I emailed every year, like, okay, they rejected me in my second year. I emailed them again in the third year, for example, like that. Um, but counting all of that together, I think over the span of 4 years or so, there were like 500 plus emails. So
Wow.
about 100 emails per one or two successful. responses. So it is also because when I started off, I was not so good at emailing. I was terrible. My CV formatting was also not good. Over the years, I learned how to improve it by asking people, because I was also not asking anyone. I was just doing whatever I thought was making sense. Uh,
So according to this, like your CV should have a format before sending that CV to professor.
yeah, I mean, it should just be something basic. You can see basic CV formats online as well. Uh, Basically, it should have all your information available. It should not be too cluttered. Maybe ensure that if you're whatever you're putting is factually correct, is grammatically correct, and everything, and all your basic information, your education, if any relevant skills that they should really know about, any relevant experiences you had, they really should know about, and if nothing else, at least something to show that you have like you are putting effort into anything you are interested in. So even at the end, if you stick a section saying that, okay, extracurricular activities, I organize this, or I play this sport, or I play this instrument or something, that is also fine, because it shows that you are putting effort into your interests. And if nothing else, something at the end like this is at least would be seen positively. It would not at least be seen negatively.
Yeah, so thank you for summarizing it. I'm sure many undergrads will find this helpful. So now, like coming to your other side, that is poetry side and like music side. So
Hmm.
there's this saying, medicine, law, business, engineering, all these are noble pursuits and necessary to sustain the life. But poetry, beauty, romance, love, music, these are what we stay alive for. So what are your views on this?
Uh, yeah, that is definitely nice to say. One thing I would add is that I think the one of the things that people at least were like we sometimes forget is that even in science, like what we are doing is essentially it has a certain beauty to itself that we are able to appreciate, and that's why you it's often the case that if you'd see that people who are engaged in science are also fairly engaged in something, say like music or something creative on the side, because um, in the end it becomes such a thing that yes, there is a beauty in the kind of understanding of nature of the universe that we are able to find, and uh, there are different ways to explore this beauty, different ways to express it. There are more cohesive, more systematic ways to do it, and that is science. But there are also more ways which may not make the most sense, but they are also something that are important for conveying how one is feeling about this the whatever we are seeing around us, or about reaching out and creating the uh, human bonds that we have, because in the end even science is built on a pursuit of people collaborating together, and such bonds are strengthened by our pursuits of activities that are our own ways of reaching out or of expressing ourselves. And thus I think it is definitely very important. And at least what I've seen around me is that scientists do put a lot of effort in ensuring that they have some kind of a creative output or some kind of way to do things beyond just science. And uh, this brings a sense of balance, which is very important in anything we do. We can never be isolated in our work. There is always many dimensions to it. There are many ways we connect with the world around us, and it is important to be aware of all of those sides of things. And that is something that I think even just doing science, you gradually realize that you are getting isolated. It's better to stay connected and not isolate yourself.
Yeah, yeah. Science is some kind of art itself.
Yeah.
So I think from looking at your profile picture, I can see you are holding a guitar.
Yes.
So there is a huge history in physics of music. Like there are lots of scientists who are musicians, like Einstein and
Yeah.
I think Satyendrath Bose was also, and CV Raman was just like legendary.
Yeah.
He has a like whole book on classical music, I guess.
Mm-hmm.
So I think before moving, so I have a few questions, like just one word answer questions.
Yeah.
So like science or poetry.
Huh. Then science. Yeah.
So favorite telescope.
I didn't catch you.
Favorite telescope. Favorite telescope. What's your favorite telescope?
Uh, that is a very hard question. We have, but right now, I think I'm legally obliged to say LOFAR because that's what I've been using.
Yeah, you are working with it. So night sky or morning light.
Night sky, definitely.
Okay, so I think we can move. So okay, so before, so can you suggest some books for undergrads, like not course books,
Yeah, yeah,
but like
yeah. I mean, there are definitely like a lot of variety of books out there, but in particular, I would say that. For example, if someone wants a popular science book on these kind of things, there's a book called First Light by Emma Chapman, which is very easy to read. And
yeah,
there are also like some which summarize how like everything that we talk about in cosmology. Like there's The Big Bang by Simon Singh, which is very nice. Then there are of course more famous books by Sean Carroll, um, even Neil deGrasse Tyson, Carl Sagan, which are very nice just to get a flavor of things. And there are also various YouTube channels out there which talk about different things in astrophysics. Uh, of course, there is PBS Space Time. There is also things like Kurzgesagt, which is a German channel for just for science, but they also talk about some things in astronomy. But there are also some which are by astronomers themselves. There is one called Cool Worlds, which is a very nice YouTube channel about exoplanets. And then there's I think Dr. Becky, an astrophysicist in the UK, who also talks about basically the daily lives and experiences of an astronomer. So not just books, but even YouTube has a lot of resources now to just get an idea.
yeah, YouTube is full with all the PhD level things. So I think anyone in the audience have question, because you guys are staying all with us. So if you have any questions, you can send us speaker request, so you can just talk to him if you have any. Otherwise, we will move into the end of this session. So Rohit, if you have any question, I think someone from comment section is asking, can I join? Yes, you can join.
Yeah, so we have
Otherwise,
one
we will.
question from YT. So, they are asking, explain why we don't need any dark matters or dark energy to explain observations.
I mean, technically we do need it. So what we, but what we understand from dark energy for dark matter is that it doesn't seem to interact with photons. It doesn't. It only interacts gravitationally. But when we want to have a model which is uh, of the universe to be able to compare it with observations, we do need to take dark matter into consideration. So, for example, in polar, what I did was we first run a dark matter simulation and then add ordinary matter and radiation on top of it. Similarly, for dark energy, we can, of course, put it in a slightly simpler manner because it's just an accelerated expansion of the universe, but it does have a very big impact on how we look at observations. And there have, in fact, been suggestions that the way the dark energy is affecting observations could mean that what we knew about dark energy was slightly wrong. We don't know yet. Like this was not. This is still not verified. People are still trying to analyze the data a bit more, but dark energy definitely impacts how you would see the structuring of the large scale structuring of the universe, how matter clusters and everything, and it does have an impact on observations, and we do take it into consideration.
So yeah, I
Yeah.
think one question I'm getting from tutor. So he's asking regarding the PhD astro in Europe and USA.
Yeah.
So he's asking like, is getting a PhD in Europe harder than getting a PhD in USA? Also, like, what are the entrepreneurship opportunities in space and astro?
A PhD opportunity, honestly, it depends more on the like a few things. It depends on how many people are applying to a place. So if it is a more famous place where typically people apply more, then it's just more competitive. It doesn't really matter whether it's in Europe or in the US. Um, Typically, in the US, even in the past, not even now, they have had a lot of times that the funding is limited, especially for international students. So while for in Europe, what they have is that the funding often does not have a citizenship requirement attached to it. It is just given as is. So while it is extremely competitive, and even in Europe, for example, in the Max Planck Institutes, is very hard to get in. If the funding scenario is to be looked at, it's slightly better in Europe. So that's something one can consider. As for innovations and such, like I space technology is not something I know the best about, but if you have like, say for example, any interesting ideas, you could always like work on it. There are like these incubation centers, accelerators and such, which universities have for promoting innovations, providing resources like just office spaces at the bare minimum, but also laboratories if needed, to essentially test ideas and then make it, build it to be marketable, to connect with people who can invest and things like that, and also connect you with essentially government sourced programs which fund the initial seed fund phase for such startups. Uh, and that's a lot of things. Like there are the like people who have essentially quit astronomy and developed their own stuff. Sometimes it's not even space tech or astronomy related. There is at least one professor that I know started his own, I think, online app for selling fashion clothes and stuff like that. So it's very random.